All right, so I am now recording. This is Tuesday, April 21st, and we are going through, I gave you guys, I wanted you to work on the 2016 free response questions, problems 1, 3, 4, and 5. 1, 3, 4, and 5. So first of all, let's hear it. How was that? 1, 3, 4, and 5. So you guys are looking for 1, B, and D, and then 4, but pretty much they're okay. But here's what I really want you guys to start looking at. Not just like, okay, this is the problem and going through, but take a step back and say, based on all of the problems that we have gone over, what are the similarities? Oh, this one is, based on the graph, and we have to, do these certain things. This is based on a table of values, and they ask us to approximate or whatever these things. Oh, this is from a function that is the rate at which something is, happening, and then we have to go through those. So I think that's a valuable thing, is to see what the typical AP type free response questions are. So let's kind of dive in a little bit. Arian asked for 1B and 1D. Just really quickly, let's check that out. And then we'll move on. It looks like a lot of you guys have questions on 4. So I'm going to just minimize this just a little bit. Okay. This is talking about water pumped into a tank at a rate. So the rate is W of T. Water is removed from the tank at a rate of R of T. So again, we have a leaky bathtub problem. This is the rate at which water is pumped into the tank, and this is the rate at which water is being removed from the tank. But they don't give this as a function, they give this as a table of values, but this is a rate in liters per hour, right? Use a left Riemann sum with the 4 subintervals to estimate the total amount of water removed from the tank during the 8 hours. Okay, so what we're looking for is, just if I were to do this, this is going to be 0, 1, 3, 6, 8. So we go up to 1340, and this would be a left-hand sum. So we go on the left up to 1340, 1340. And then at 1, we'd go up to 1190, 1190, right? This one, we'd go up here to 950 and then to 740. So it would be like this. So basically, it's going to be 1 times that. So 1 times 1340 plus 2 times that. 2 times 1190 plus 3 times that. So 3 times 950 plus 2 times that. 2 times 740. And that's going to give us the approximation that they're looking for B. Now, they tell us that R of T is differentiable and decreasing on the interval from 0 to 8. So if we have a decreasing function, and we're using the left-hand approximations, is that going to be an over or under approximation? My gardeners are here, and that's exceptionally loud. That's going to be an over approximation, right? Good. Hold on one sec. Okay. So, so that was that, and then, okay, let's, I want to look at a little bit of the, scoring guideline right here. When you do that, you get 8,050 liters. That is an overestimate because R is a decreasing function. All right, cool. Okay, so then the next part of that was, oh, I could go here. 1D asked for, is there a time when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Hold on 1 second. I'm sorry. Okay, so so what we need to see is that W of t is greater than R of t at some point, and W of t is less than R of t at some point. And then that would give us, enough information to determine, because we do have that, of course, W of t is continuous and differentiable everywhere. And R of t, they tell us, is differentiable, therefore continuous and differentiable on the interval. So if we had that W of t is greater than R of t for some value, and W of t is less than R of t for another value on here, which is really W of t minus R of t is greater than 0, and W of t minus R of t is less than 0 at certain t values, then that would be enough information to determine that that they were exactly equal to each other at some point. So let's see what they have for that. Oh yeah, they say that at t equals 0, W, so the rate at which water is entering, is greater than the rate at which water is exiting. So W of 0 minus R of 0 is greater than 0. And then at 8, so t equals 8, the rate that water is entering is less than the rate that water is exiting. And so, by the intermediate value theorem, this is like that problem that we did, I think, last time. There must be some value in between 0 and 8 where they're equal to each other. Okay, cool. Okay, so that was 1. And then you guys are looking for a lot of 4s. So let's check out 4. 4 is this guy. Okay, good. We have an Euler's method problem here. So again, let's do this. Let's minimize a little bit. I'm actually going to put this in a new page. So here we go for number 4. Okay, so let's just do this whole thing. So for A, okay, it's asking for the second derivative, but the thing is, dy dx is in terms of both x and y. So really, if I'm taking the derivative with respect to x of dy dx, this is going to be the derivative with respect to x of x squared minus 1/2 y. So this is just equal to, so the derivative with respect to x of x squared is 2x. The derivative with respect to x of 1/2 y is 1/2 times dy dx. But this is known as 2x minus 1/2. Dy dx was given to us. So we would say dy dx is just x squared minus 1/2 y. So we would say that the second derivative with respect to x is negative 1/2 x squared plus 2x plus 1/4 y, right? That's what the second derivative of y with respect to x would be. So you had to use implicit differentiation for that. Okay, next, part B says, so let me go to blue for B. Let y equals f of x be the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph of f have a relative min, max, or neither at the point -2, 8? Well, first of all, let's check this out, right? Okay, so for B, -2, 8 is on the graph of y. What they're asking for is, first of all, determine if the derivative is either equal to 0 or undefined at -2, 8. Why do we need that to be true? What happens, or what did we learn about wherever the derivative is equal to 0 or undefined? What does that give us? If the derivative is equal to 0 or undefined, what do we know? Okay, those are critical numbers. And what do we know about critical numbers?
There could be a local max, a local min, or neither at everyone.
Those are the only points where there could potentially be a local max, local min, right? But it also could be neither of those, like you said, right? But those are the only points where there could potentially be a local max or local min. So let's find dy dx evaluated when x equals -2 and y equals 8. So remember, dy dx was equal to x squared minus 1/2 y. So this ends up being -2 squared minus 1/2 times 8, which is 4 minus 4, which is 0. So here I have that the first derivative is equal to 0 there. That's a good start, okay? But by no means do we know that the derivative, that the function has a local max or local min there. But now we have the second derivative. So we know that at this point right here, -2, 8, the first derivative is equal to 0. So let's check out the second derivative. Why are we checking out second derivative? Because remember, if the first derivative is equal to 0, there are 3 possibilities there. Well, there's maybe more than 3, but either there's a local min if the second derivative is negative. So I'm going to put y double prime less than 0. And this is y prime equals 0. Y prime equals 0. And, oops, I should move that down here. So it could look like this. So y prime equals 0 and y double prime is greater than 0. So sorry, I said min. This is a local max. This would be a local min. Or it could be either like a straight line, or it could be something that looks like this, where the derivative is 0, but so y prime equals 0 and y double prime is also equal to 0, or potentially doesn't exist or something like that. So this is no max or min. This gives us a min, and this gives us a max. See, so we're looking for the second derivative. Is the second derivative going to be greater than 0, in which case there's a min? Second derivative less than 0, in which case there's a max. So we have the second derivative right here. So let's go ahead and find the second derivative of y with respect to x when x equals -2 and y equals 8. And really, we're just looking to determine if that is going to be, positive or negative or 0. Now, I'm actually going to use this up there because I've already figured out that this is 0, right? That's 0 when x is 2 and y is 8, x is -2 and y is 8. So this whole thing is 0. So when x is -2, I get that the second derivative is going to be -4. Now, if you don't believe me, you could plug it into, this long thing that I have underlined in red, but you should get -4, which is less than 0. Gosh, which is less than 0. Therefore, because the first derivative is equal to 0 at -2, 8, and the second derivative is less than 0, there exists a local max at that point. Let's see for parts A and B what they have on the scoring guidelines. Here we go. Okay. A and B. So we have for A, we have, the second derivative of y with respect to x in terms of x and y is equal to that, which is what we got. And then for B, we have that dy dx evaluated when x equals -2 and y equals 8 is equal to 0. And the second derivative is equal to -4, which is less than 0. Therefore, f has a relative max at the point. Does that make sense to you guys so far? I feel like we need a session where everybody's talking. I'm gonna do that. Hold on. Unmute all. What's up, guys?
Hello.
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 Hi, I guess.
This is so much better. I mean, it's weird because in class I want you guys to be quiet, but like now you've been quiet for such a long time.
Yeah, make up your mind, Growler. Jeez.
Well, I have. I
So,
made up my
you
mind.
should unmute him.
In my classroom, I want you guys to be muted. When I ask you guys a question or like, hey, does that make sense? And I hear absolutely nothing. Like in class, I see like, or like, right, and I can't read you. I can't read you when you're, okay, I'm gonna mute you again. Say bye.
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 I mean, not really bye. I mean, stay here. But
No, I'm going. See ya.
no,
Yeah,
stay.
me too.
No, please stay. Just mute. Okay, good. Okay, so I felt like there were actual people there and I wasn't just staring at my computer screen for a hot minute. Okay, next. Part C. Oh no, there's a limit, right? Is probably what's going on in your head. So let y equals g of x be the particular solution to the given differential equation with g of -1 equals 2, okay? So first of all, don't think to yourself, wait a second, if they said that dy dx equals this, and they already said that this was, it went through this point. There's a particular solution that was f of x where it went through that point. Now they're saying there's another another equation y equals g of x that goes through that point, -1, 2. Remember, this was my analogy in class about going to like a stream with my brothers, going hiking or something, and I put you know, we'd have races with our little sticks and they'd go down and whatever in the paths, right? So remember, and with differential equations, we also talked about like slope fields and how it kind of like, there's one, if you just go this way, it might veer this way. And if it goes this way, it might veer that way. So there are infinitely many solutions to this differential equation, right? That's where the plus c comes from. So there are a family of functions, right? So they're saying f of x is one of those, and it goes through the point -2, 8, along with many other points. And then they say g of x is another solution, and it goes through the point -1, 2, right? And so that's what we got going on. So anyway, then they say, find the limit as x approaches -1. So I'm going to do it up here, and I'll use green. So find the limit as x approaches -1 of g of x minus 2 over 3 times quantity x plus 1 squared. Okay, so when we just plug in -1, using direct substitution, we have 2 minus 2, right? I have 2, g of -1, they tell us right there is 2. So 2 minus 2 is 0, so I get 0 divided by. And when I plug in -1, I get -1 plus 1, which is 0 squared is 0 times 3 is 0. Oh no, I get 0 over 0. Ah, I can't do this limit. But really, we say, oh, I can do this limit. I just have to apply what? Somebody talk to me. Don't just chat it. Don't type it. Say it.
L'Hopital's rule.
Yes. L'Hopital's rule, right? Because I have an indeterminate form. So I know that this thing is equal to the limit, by L'Hopital's rule, right? The limit as x approaches -1 of g prime of x over, now it's the derivative of that. The derivative of the denominator is going to be 6 times quantity x plus 1 to the first power, right? Times 1. Okay, now, g prime of x. Well, how am I supposed to know what that is? Well, remember, g of x was the solution to this differential equation. So that means that g prime of x is equal to that. So really this thing is equal to the limit as x approaches -1 of g prime of x, which is x squared minus 1/2 y over 6 times x plus 1. Okay. So this is at the point -1, 2, right? Because that's what they gave us right there. I'm kind of hiding it. At 1, 2, or -1, 2. So at -1, 2. Now when I just try to plug in those values, I get -1 squared, which is 1, minus 1/2 times 2, which is 1. 1 minus 1 is 0, over, I plug in -1 in for x, and I get 6 times 0. So I get 0 over 0. Oh no. So guess what I have to do? What do I have to do?
L'Hopital's rule again.
Yeah. Is equal to, by L'Hopital's rule, the limit as x approaches -1 of something over, what's the derivative of the denominator now? You could distribute that through or whatever, but what's the derivative of the denominator?
6.
Bam. Right? Because up here it was 6x plus 6, so the derivative of that's just going to be 6. Now for the numerator, it's going to be the derivative of this thing. But guess what? They had you do that already in part A, didn't they? So it's this that I have in my blue box. Remember, this is the second derivative of y with respect to x. So I'll just put maybe this there. So 1/2 x squared plus 2x. I have right here. So -1/2 x squared plus 2x plus, what just happened? Uh-oh. I don't know if you guys just saw that. I don't think you did. Good. I'm going to move this guy down there. Plus 1/4 y. Okay? And now when I plug in, remember this is when, -1 comma 2. So this is equal to, so x is approaching -1 and y is approaching 2. So this gives me -1/2 plus -2 plus 2 over 6, which is -1/12. Okay, so that's what we got going on there.
I think you messed up somewhere because the answer was -1/3. I
Oh,
didn't see
bummer.
it.
Let me see what I have going on. Second derivative. -1/2. Oh, I see it. I'm plugging in 2 for y right here, and it's 1/4 of 2. So that becomes 1/2. There you go. So that positive 1/2 and the negative 1/2 cancel out, and I'm left with -1/3. Is that right?
Yeah.
Yeah. So that was -1/2 minus 2 plus 1/2. So those guys cancel out, and I'm left with -1/3. So let's see what they got going on for that. Problemo. Using L'Hopital's rule, we get that. Okay, so that was a 3-pointer. And now we get to part D, which is Euler's method. So I kind of want to do, I'm going to do this. So I have a fresh page for this. Whoops. Okay, so now it has a third function that is a particular solution. They're telling us y equals h of x is the particular solution. And now this tells us that h of 0 equals 2. So I'm starting at 0, 2. Okay? And now it says use Euler's method starting at x equals 0 with 2 steps of equal size to approximate h of 1. How many of you guys remember, how many of you guys don't remember Euler's method? If you don't remember Euler's method, unmute and I want to hear you.
I don't.
remember
I
doing
don't.
it, but not how to do it.
Yeah, not particularly.
I don't remember.
Not really.
Okay.
I do not remember.
Here's what we got going on, okay? Remember we used our calculators, and maybe I'll bring the calculator up and show you how to use a calculator, but you wouldn't even need to for this because it's only 2 steps, which I would never expect it to be like more than 4 steps. Even 4 would be kind of excessive on the AP exam. But anyway, here's what we did, right? We have n x sub n, y sub n, and dy dx evaluated at x sub n, y sub n. I'm gonna bring these guys up here. Okay, and this was the big thing over here, was that so y sub n plus 1 is equal to, so the next y value is equal to the previous y value plus, let me get rid of this thing. Move this down. Plus dy dx evaluated at x sub n, y sub n, times h, where h is my step size. Do you guys remember that now? A little bit, maybe? Whatever. Okay, so I'm going to plug in what I know right now. I know, okay, start with n equals 0, and then I want 1 and 2 steps. My initial x value is 0. My initial y value is 2. And let me write the differential equation in with the blue just so I have it here, which is x squared minus 1/2 y. This is dy dx, right? And so when x is equal to 0 and y is equal to 2, what is my dy dx equal to? Someone say.
-1.
Or -1.
Whoever spoke first, it sounded like you were auto-tuned. It was like, -1. Anyway, all right, so that's -1. So what I'm saying is, this is now going down here for my x values is just the next step, which if I start at 0 and I'm going to 1 and I'm using 2 steps, the step size is going to be 1/2 because it's just b minus a over n. So b minus a over n, where b is 1, a is 0, and n is 2. So there's 1/2. So anyway, this is going to be 1/2 and 1, right? Now, my y sub 1 equals y sub 0 plus dy dx evaluated at x sub 0, y sub 0 times, and this is just going to be 1/2. Okay? So, gotta move this again. Gosh. There we go. Can I place that up here? Here we go. Okay. Okay, so this tells us that y sub 1 is equal to y sub 0 is 2 plus dy dx at x, x naught y naught is -1 times 1/2. So this is 2 minus 1/2 is known as 3/2, right? So that goes here, 3/2. Now we're looking for this, which is using this differential equation when x equals 1/2 and y equals 3/2. So calculate that for me. When x is equal to 1/2, I have 1/2 squared, which is 1/4 minus 3/4. 1/4 minus 3/4 is known as what?
-1/2.
Good, -1/2. So now I know that my y sub 2, which is what I'm looking for, right? This is my the whole point of me doing this is to get that answer right there. So y of 2 is equal to y of 1, which was 3/2, plus dy dx when x is equal to 1, at x sub 1, y sub 1, which we just figured out was -1/2, times my step size, which is 1/2. So maybe I did that too fast. So let me go down, bring this down. Where's that stuff coming from? This is coming from the fact that y of 2 equals y of 1 plus dy dx evaluated at x sub 1, y sub 1 times 1/2. And now I've just plugged in all of that. Y sub 1 is 3/2. This is just that guy, which is negative 1/2. And that's always going to be just the step size, which is 1/2. So that gives me that y sub 2 is equal to 3/2 minus 1/4, which is known as what? 5/4. Right? Cool. So now, let me see if I answered it. Use Euler's method starting with 2 steps of equal size to approximate h of 1. So I'd say, therefore, h of 1 is approximately 5/4, right? Bam. Cool. Let's go and see what they have on the scoring guidelines for that guy. Just a little 2-step. So h of 1/2 is 3/2, and h of 1 is approximately 5/4. Okay. So that's how to do Euler's method by hand. Do you think it would be beneficial for me to show you how to use your calculator? You will have your calculator. Step size. So the step size was this was my initial x value. So my initial x value was 0. I was going to, they want me to approximate 1. So this is like your A value, and that's like your B value, okay? They tell us that 2 steps, this is n equals 2. So 1 step, 2 steps. We can see that each step is going to be 1/2. For more complicated problems, we would just say that step size, which oftentimes we call h, is b minus a over n, which in this case is 1 minus 0 over 2, or 1/2. All right? All right. Do you want me to get out my calculator and show you that way?
Yeah, that would be helpful.
All right, let's do it. Let's do it. Where are you, calculator? Bam. All right. So this is what I did. To make it so it's a little bit easier, especially if you have to do a whole bunch of different, iterations. Under y sub 1, I plug in my differential equation. So that happened to be, they gave us that the differential equation was x squared minus 1/2 y. But instead of using x's and y's, remember how I used a's and b's? So that's a squared minus 1/2 b. So let's do that. A squared minus 1/2 b. Okay? It's second quick. Now, I'm going to set a equal to my initial x value. That's 0. And b as my initial y value. My initial y value that they gave me was 2. Okay, so now what I'm going to do is I'm going to say that my new y value is going to be my previous y value plus vars, y vars function y1 times 0.5 times my step size. So I'm saying that my new y value, or sorry, this right here is going to be my new y value. It is the previous y value, so 2 plus, remember this is my differential equation with my initial x and y values times my step size. So when I hit enter, I see that that is 3/2 or 1.5. I'm now going to make that my new y value, which I'm calling b. And I now need to make my new x value, or a, 1/2. Because I'm going up a step on my x values. And then you go up to this guy, and you do that, and it gives us 1.25. So by doing it one time, I got 1.5. By doing it a second time, I got 1.25, which is also known as 5/4, which is my my answer. Five-fourths, 1.25, right there. Okay, so that's the way I do it. Again, b plus, so remember b is my previous y value, plus y sub 1 is really my differential equation with the x and y values that I've put in there for my initial, times the step size. That gives me my y sub 1. I call that my new b. So this is now my new y value, and 0.5 is my new x value. So now my y sub 2 is going to be y sub 1, or my first y value, plus the differential equation at my new x and y values times the step size to give me that. Anyway, that's how you use your calculator to do that. All right. Rock and roll. So we are out of time. Here's what I want, and I'll put this in the Google Classroom. I want you guys to now focus on the 2015 FRQs. And I want you to do problems 1, the rate at which rainwater flows into a drain pipe, blah, blah, blah. The pipe is partially blocked, allowing water to drain out the other end of the pipe at a rate, blah, 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 right? So you can see it's the same type of problem. But anyway, so 2015, you're going to do problems 1, skip 2, because that's parametric. 3, oh, look, a table of values, weird. 4, differential equation, slope field 1, cool. And 5, this one's not too bad. Don't, like, you look at K and you're like, but they tell you K equals 3, K equals 4, oh, whatever. So anyway, so 2015, problems 1, 3, 4, and 5. That's what you're focusing on, and I want you to have that done by Thursday so we can discuss those on Thursday. Again, you have the scoring guidelines, there, and you also have, if you just do any search or, on YouTube, they have gone over the solutions and there's someone actually working them out. So you could check that out as well. But 2015 AP Calc BC free response questions, problems 1, 3, 4, and 5. Cool? Yeah?
Cool.
Coolio, Fulio. All right. Other than that, man, hey, it's going to be beautiful starting today for like the next week plus, like 11 days or so. Enjoy it. Get some sun, some vitamin D, go outside. Do something active. Let the sun bring warmth to your soul. All right, guys. I'll see you guys on Thursday, 10:30. If you have any other questions, you could hang on for a little bit and ask. Don't forget, like I said, you guys got an email. Try to find out if you could do anything on, with that to make sure or confirm that you still are taking the AP exams. All right. Cool. Bye, guys. Have a great day.
Bye, girl. Have a good one.
All right. You too.
Be well.
All right. Kayla asked for 5C. I can go to 5C real quick. C. I was on 4. Let's check it out. We have the funnel contains liquid that is draining from the bottom. At the instant when the height is 3, the radius of the surface of the liquid is decreasing at 1/5 inch per second. So that tells me that RDT is negative 1/5 inches per second at that point. At this instant, what is the rate of change of the height of the liquid? So I'm looking for the HDT. Well, they give us that, so here's what we have, right? If I just implicitly differentiate this with respect to time for C, so R equals 1/20 times 3 plus H squared. Let's differentiate with respect to time. I get dRdt equals, over here I have, so let's just do this. That's going to be 3/20 plus 1/20 H squared, right? So differentiating that with respect to time, the 3/20 goes away and I'm just left with 1/10 H times dH dt. Now they said H was equal to 3, and they're looking for dH dt, and dr dt, they told us, is negative 1/5. I'm not going to put units in there because I'm just doing this quickly. So this is, you multiply both sides by 10/3, I get the dH dt is equal to negative 2/3. And that's going to be inches per second. So H is decreasing at negative 2/3 inches per second, something like that. Let me see what the question really was. Rate of change of the height of liquid with respect to time. Well, that's going to be negative 2/3 inches per second. Let's look at the scoring guidelines just really quickly. Yeah, that's all it is. They have this negative 1/5 equals 3/10 dH dt, just like I had. Does that make sense, guys?
Yeah.
All right.
Thanks.
All right, y'all. Have a good day. I'll see you guys.
Have a good day.
All right, you too.